Alright, in this example, we're going to be finding the electric field given by two infinitely large sheets separated by a distance d. So, in doing this example, let's first find out the direction of the electric field. We know that when you have a positive charge, oh, by the way, I'm sorry, I forgot to note this. This sheet has a positive charge distribution, whereas this sheet has a negative charge distribution. Very important. Alright, so we know that if you have a positive charge, your electric fields are directed away from it, perpendicular and away from it. So in this case, we have an electric field going like this, and an electric field going like this. Away from the positive charge. Now, we must do the same thing with the negative charge. If it's a negative charge, what happens is the electric fields go toward it. So, in this case, on this side, the electric field will go towards the negatively charged disk, whereas on this side it will go in the opposite direction. Alright, so if you notice here, we have opposite vectors here and opposite vectors here. So they cancel each other out. So in the end, what we really care about is the electric field that's on the inside here. And that's going to be given by the electric field of the positive charge and the electric field of the negative charge. So you may be asking, well, doesn't distance have something to do with it? Well, if you recall from the last video, we found that the electric field of an infinitely large sheet is given by the charge distribution divided by 2 epsilon naught. So it is not dependent on the distance away from the sheet. So the electric field is constant here, here, and here. Here, here, here. It's constant for both of these sheets. So now, let's find what the electric field is here. We know that the electric field of positive Q is equal to sigma over 2 epsilon naught. And we also know that the electric field for the negative distribution is the exact same thing, except in the opposite direction. However, if you notice, these vectors are pointing in the same direction. So therefore, we just take the magnitudes and add them together. So in other words, when we add these two, we just take the magnitudes. So the electric field is equal to the magnitude of this, which is that, plus the magnitude of that, which is this, same exact thing. And we get that the electric field is equal to sigma over epsilon naught. So if we were to reevaluate this, here are two sheets. There would be an electric field of 0 here, an electric field of 0 here, an electric field of sigma over epsilon naught going in this direction. So another thing to note is that the distance separated, oh, I'm sorry, that was my bad. I'll repeat that. The electric field here and here are 0, and the electric field inside is equal to sigma over epsilon naught in this upward direction, going from positive to negative. And an important thing to note is that distance did not make a role here. So you could have had these sheets an infinite amount of space apart, or you could have had them virtually right next to each other. It wouldn't have made a difference. The electric field would always be sigma over epsilon naught. The importance of the distance separated by d will come into play when we deal with capacitance, but for now, just know that electric fields between two parallel sheets is going to be constant.